The basic idea behind structural equation modeling is that most, if not all, measures that we use in the social sciences, such as questionnaires, items, tests, ratings, and so on, contain measurement error, or in other words, they are not perfectly reliably measured. Not all of the variability that is captured with our measurements reflects so-called true score variance or reliable variance. And so this can cause problems for statistical analyses, because we know from measurement theory that unreliability or random measurement error can lead to biased estimation of the associations between variables, such as, for example, biased estimation of Pearson product moment correlations when we want to analyze relationships between different test scores. Then the correlations are underestimates when we have measurement error. It can be shown by test theory that when measurements are not perfectly reliable, then the correlations between observed test score variables reflect underestimates of the true score correlations. And the same is true for regression coefficients when we use, for example, linear regression analysis and we use observed variables, test score variables that are contaminated by random measurement error, then also the regression coefficients can be biased. Now, when we are analyzing more complex relationships between variables, where we look at larger models where we have multiple independent variables, multiple dependent variables, then the direction of the bias can be difficult or impossible to predict. With bivariate product moment correlations, we know clearly that we will get underestimates of those correlations relative to the true score correlations. But with path coefficients in more complex regression models, multivariate regression models, it's not always clear whether the resulting effects will be underestimated or overestimated, and so therefore this can cause us a lot of trouble. Also, measurement error leads to a bias in standard errors, and in statistical inference, meaning tests of statistical significance, are also incorrect. Confidence intervals are incorrect when we have measurement error. And so in structural equation modeling, we address this issue of measurement error by introducing latent variables that reflect true score variance. So we can define latent variables through measurement theory, as we will see, in such a way that these variables are connected to our observed variables and represent, so to say, error-free versions or error-corrected versions of the observed variables. And so in that way, we can then look at associations, correlations, regression coefficients between latent variables which are not contaminated by measurement error. And this is probably the primary reason, the most important reason for using structural equation modeling, is to get the measurement error problem under control and estimate relationships between variables without bias. So how does this work? The first ingredient to structural equation modeling is path analysis. Now, path analysis can be thought of as a type of multivariate regression model in which you have multiple dependent variables. In multiple regression analysis, we have one dependent variable, we have multiple independent variables or predictor variables. In path analysis, we can simultaneously have multiple dependent variables and multiple independent variables. And also, variables in path analysis can be dependent and independent variables at the same time, which means there can be so-called mediator variables, where one variable causes another variable and then that variable causes another variable, as we will see. So we can analyze quite complex relationships with path analytic models, much more complex than with multiple regression, where we only have our set of predictors, we have our one outcome variable, we estimate the regression coefficients and an R-squared value for the dependent variable. In path analysis, we can actually estimate the relationships between multiple dependent variables simultaneously, multiple path coefficients, multiple R-squared values. We can look at direct and indirect or mediated effects in path models. So it allows more flexibility in modeling complex relationships between variables. I want to give you an example first of all, so you can better understand what path analysis is about, and I'll begin with a conceptual example, and then we will take a look at the math, the equations behind a path analytic model. It's a simple example that is based on work by Whitelaw and Liang in the area of health psychology, where they looked at relationships between subjective health. So that would mean, so say, a person, how they rate their own health subjectively, physical health, which indicates, so say, objective parameters of a person's health, such as, for example, how sick the person has been in the last year, how many diseases, how many visits to the doctor, how many chronic diseases, and so on. So how many health problems somebody had, and then also functional health, as we will see. So the basic idea here is that there is a relationship between physical health and subjective health. You could look at that with a bivariate regression model. Physical health predicts subjective health. So if I have health problems, then typically I will rate my subjective health lower than if I don't have health problems. And then in the path analytic model by Whitelaw and Liang, there is a third variable, which is functional health. Functional health means how you function, so to say, stated in simple terms. So, for example, whether a person is able to manage their daily lives, whether they can climb stairs, whether they can drive a car, whether they can do work in the garden, cook, and so on. So the functioning of a person. And so the idea here is that physical health may or may not affect subjective health directly, as shown here by this path from physical health to subjective health, but there might also be an indirect effect via functional health, such that persons who are more sick tend to have lower functional health, and then functional health is something that makes them unhappy, or lack thereof. So lack of functional health would make them potentially depressed, or would make them rate their subjective health lower, obviously, when they see that they cannot do the things that they normally were able to do. And so there could also be a mediated effect of physical health onto subjective health via functional health. And so in a path analytic model, we can estimate those different paths simultaneously. So in more formal terms, we have in such a model here an exogenous variable x, we have a mediator variable m, and we have an endogenous variable y, or a dependent variable. And so you can see m is also a dependent variable because m depends on x, and we can simultaneously consider the two dependent variables m and y in this model, unlike standard regression analysis where you would have only a single outcome variable. In path analysis, you could have a lot more variables. So you could have additional mediator variables, you could have additional outcome variables. For example, after Y subjective health, you could have another variable that is depression or anxiety that is then predicted by a lack of subjective health, for example. So you can have quite complex systems of regression equations that are all estimated simultaneously. And so in such a model, we estimate path coefficients, beta 1, beta 2, beta 3 between these variables. Those are simply linear regression coefficients. And we have residuals or error variables, epsilon for the mediator, epsilon for y, because there is variance in m and y that is not accounted for by the independent variables. In this model, there's residual variability that is due to other factors and or due to measurement error. And so this is basically a two-equation multivariate regression model where y has a regression equation, y is dependent on x and m. You can see that paths are emitted from both x and m towards y with the regression coefficients beta 1 and beta 3. So those are the regression slope coefficients, or path coefficients as we say in path analytic terms. And we also have an intercept beta 0 y, which is not shown in the path diagram. So this is a simple linear regression equation with 2 predictor variables. And then the second equation is for m, because m is also a dependent variable. M in this case is only dependent on x. So there's just an intercept beta 0 m, and there's a slope coefficient beta 2 for the regression of m on x, and there's an error variable epsilon m, because m also is not perfectly determined by x typically. And so what distinguishes path analysis from multiple regression again is that we estimate those 2 equations simultaneously. The parameters of these models are all estimated in one step when you run a path analysis. Now, you could do this. You could use a program for structural equation modeling such as lavaan to estimate those path coefficients in a single step. However, you still have the problem that there is measurement error in x, m, and or y. So probably physical health is not measured with perfect reliability. Subjective health, self-rated health for sure isn't measured with perfect reliability, and functional health. Also, we have to expect that there's a measurement error. There will typically be questionnaires involved, or there will be physical parameters that are measured, but that are typically not perfectly reliable. And so then as a result, the path coefficients beta 1, beta 2, and beta 3 might be biased because of measurement error. And so therefore we need a second ingredient to adjust those coefficients or get estimates of those coefficients that are not biased. And so the second ingredient for a structural equation model is confirmatory factor analysis. Confirmatory factor analysis allows us to connect our observed variables, the measured variables or indicators as we say, to so-called latent variables. The latent variables are corrected for measurement error. And so we're using measurement theory to define measurement models that can then be estimated as models of confirmatory factor analysis. And with these measurement models, we connect our observed variables to latent variables. So we formulate a theory about how latent variables are measured by which observed variables, so which observed variables can be used as unidimensional measures of a common factor, as we say, or common latent variable. And then that allows us to make adjustments for measurement error. So the basic idea behind confirmatory factor analysis is that there are multiple measures of each latent variable. So say repeated measurement of the same attribute with multiple independent measurement devices, multiple items or multiple reports or multiple different variables, as we will see. And then this allows us to account for error. So say this repetition allows us to take into account that the measures may not agree perfectly, and then if they don't, then this is, so to say, what we see as measurement error, conceptually speaking. So this allows us to take the measurement error problem into account and also to estimate the reliabilities of the observed variables, meaning quantifying how much of the variance or what proportion of the variance that is reflected in a measure is true score variance versus measurement error variance. So we're relying heavily here on measurement theory for defining latent variables, such as classical test theory. Classical test theory is a measurement theory that allows us to define true score variables as conditional expectations of observed variables, and so therefore there's no voodoo magic involved really in defining latent variables. They're not actually that latent. They are well defined based on measurement theory, specifically classical test theory. So let me give you a conceptual example here as well, so you understand better what confirmatory factor analysis does, and we'll begin with a simple one-factor model or single-factor model where we have one latent variable. So our latent variable that we want to measure without error is one of the latent variables in our path model is physical health, our exogenous variable or predictor variable. And so this variable we might measure with an observed variable that is reflecting the number of sick days per year or in the last year for a given individual. So we could ask the individuals to rate or report how many days were you sick in the past year. And obviously that's not measured with perfect reliability because individuals may not recall, they may not have a perfect record of how many days they were sick. So there's definitely some unreliability involved here. And then as a result, we would want to have at least one other measure of physical health and not just rely on the likely not so reliable or at least not perfectly reliable measure of sick days. So for example, we might also try to get a sense for the number of physician visits that somebody did in the past year. So how many times did an individual go to see their doctor? And again, this also is probably not measured with perfect reliability. There may not be a perfect record available to the investigator, but the fact that we have two indicators already allows us to get to a little bit more towards the truth, so to say, in terms of the reliable variability. And there might be more indicators. So ideally, you would have more indicators of physical health, maybe a rating from the doctor or some other parameter, maybe the BMI or something like that, or some other measure of physical health. But in this case, for simplicity, I'm focusing on just two measures because that's the minimum requirement in order to specify a confirmatory factor analysis model. So two indicators. And so the idea is that the latent variable is what causes variation in these measures. So the reason why people differ on their number of sick days and on the number of physician visits is because there are true inter-individual differences in physical health in the population. And so therefore we see some true variability in those measures. But in addition to that, we also see some random error variance. So some of the differences that we see in the number of sick days in our data are just simply due to random measurement error because people don't recall how many days they were sick, really. And so they estimate, they guess, and so therefore there will be some error involved. And so some of the individual differences on those measures are just simply reflecting measurement error variance. So we have to take that into account. And therefore we also have epsilon 1 and epsilon 2, our two measurement error variables here that reflect the variability that is not common to the measures, that is not true score variance, whereas the latent variable physical health, here the variance for this variable is what we call true score variance or reflects true score variance. So this is based on the covariance between the two measures. They will be correlated positively, we hope, so to say, reflecting that they both measure the same common cause, the same factor, and so that covariance between those two measurements is what then conceptually speaking or roughly speaking what defines the variance or what allows us to identify the variance of the latent variable physical health. So this is how this works conceptually. Now let's take a look at the equations here. So we could more formally say that we are measuring a latent variable that we could also call a factor. And here this would be the factor F1. F1 is measured by two observed variables, y11 and y21. And there are so-called factor loadings, which are also regression coefficients from linear regression equations. And so these lambda parameters here are so-called factor loadings or regression weights that characterize the strength of association between the measure and the latent variable that it is supposed to measure. So these loadings are related to the reliabilities of the indicators. And then also we have the measurement error variables epsilon 1,1 and epsilon 2,1 that reflect random measurement error. So now we can also express this path model, this path diagram in terms of equations. Those are regression equations. Y11 is the first measure. It has an intercept, measurement intercept alpha 1,1. It has a factor loading lambda 1,1, and the factor is the independent variable in this equation. And then we have a measurement error or residual term here as well. So that would be the measurement equation for the first variable, and then we have an equivalent measurement equation for the second measure with a separate intercept alpha 2,1, a separate factor loading lambda 2,1, and a separate error variable epsilon 2,1. And so now this model can be identified by if we include certain constraints that we will discuss later in this workshop. So as such, this model would be under-identified, but within the context of a larger model and also with appropriate constraints on certain parameters, this model can be identified, meaning there can be a unique solution for at least some of the parameters of this model. And this allows us to account for measurement error, estimate true score variance, and estimate the reliabilities of the observed variables. Now, this is the second ingredient for a structural equation model. And so then the last step is to put the two together to a so-called latent path analytic model, we could say, or often people will just say a structural equation model, which is a combination of the path analytic model that we discussed first and the CFA model that we discussed just now. This allows us then to examine structural relationships or the paths between latent variables as opposed to observed variables, and to account for measurement error and estimate the reliabilities of the observed variables. Now in our case then, the path model would look like this, where now we're looking at the relationship between physical health, functional health, and subjective health on the basis of latent variables. And here we now estimate those path coefficients or regression coefficients beta 1, beta 2, and beta 3 at the level of factors or latent variables that are corrected for measurement error. In order to be able to do that, we have to have a measurement model for each variable. There are also latent residuals, which here are indicated as zeta 1 and zeta 2. So those are latent error variables for the structural regression portion. But so in order to get to the latent variables, we have to have a measurement model for each factor with at least two indicators. So you can see there are the two indicators for physical health that we already discussed, the number of sick days and the number of doctor visits. And then for subjective health, we would have also two measures at least. So we might have different items from a self-rating questionnaire or test halves or something like that, where we split a scale that consists of multiple items into two portions and have two sum scores for a given scale, and then have two measures also for subjective health and the same for functional health, where we might look at two different parameters of functional health, for example. And so in that way, we are able to separate true score variance from measurement error variance for each of the three constructs, and then we can look at the relationships between the three attributes in terms of a latent variable model, a structural model that is based on latent variables, and that allows us to estimate the coefficients beta 1, beta 2, and beta 3 without measurement error. And it also allows us to obtain all of the parameters in a single step. So the whole model with all its equations, with the two structural equations and the 6 measurement equations, is estimated simultaneously. We can test the model against the observed data because this model has restrictions, it has implications for the covariance structure of the observed variables that could be falsified in an empirical study. So a data set, so say, may or may not work, or the model may or may not fit a given data set, I should say, and so this can be tested with a test of model fit. So that's also a benefit of this analysis, and this analysis allows us to look at R-squared values for the dependent variables, functional health and subjective health, as we would be able to do in a regression or path analytic models.